All right. Now we're doing chapter 5, containers in Google Cloud. This is orchestrating workloads with Kubernetes. Today, we shift our focus to one of the most powerful and flexible tools in cloud-native development. This is containers, and more specifically, how they're deployed and managed on Google Kubernetes Engine, or GKE. Containers let you package applications with everything they need: code, dependencies, configuration into a lightweight portable unit. Kubernetes is the orchestration engine that manages and scales those containers. In this chapter, we'll explore core Kubernetes concepts, cluster architecture and administration, persistent storage with volumes, configuring networking and exposing workloads, high availability clusters, and the use of preemptible instances for efficient batch jobs. Let's begin with the basics. What is Kubernetes? Kubernetes is a managed environment for deploying and managing containerized applications. It groups multiple Google Compute Engine VMs into a cluster, where each VM is called a node, and the cluster is managed by a centralized control plane. You must package your application as a container before deploying it in Kubernetes. These deployed containers are referred to as workloads. So, Kubernetes cluster components, the brains and muscles of GKE. In this segment, we're heading into the engine room, where the control center and execution force behind Kubernetes lives. The cluster components. Okay. When you deploy an application to Google Kubernetes Engine, you're not just pushing code to the cloud, you're tapping into a robust automated system that scales, heals, schedules, and optimizes container workloads, all behind the scenes. At the heart of every Kubernetes deployment are two main types of components, each with a distinct role. One, the control plane, your central command. Okay? Think of the control plane as the mission control of your Kubernetes universe. This is not where your application runs. Instead, it coordinates everything. It's the intelligence, the conductor, and the operating system of your distributed system. Within the control plane live several critical components. API server, this is the front desk of your cluster. All external tools, kubectl or kubectl commands, and internal cluster requests go through here. It validates and configures resources like deployments, pods, and services. Scheduler. Okay. Scheduler. This determines where to run new pods based on available resources, affinity, anti-affinity rules, and the node taints or tolerations. Controller manager. This watches the state of the cluster and reconciles it to the desired state. If a pod goes missing or a node goes down, it triggers replacement actions automatically. etcd, the consistent and highly available key value store that holds all cluster configuration and state data. The control plane ensures that what you declare in your YAML files becomes reality and stays that way. For the example, understand that while you interact with the API server, you don't manage the control plane directly in GKE. Google handles it for you in standard clusters entirely abstracts it in Autopilot clusters. See the Autopilot cluster here. Set to reset you as central 1, and then you can build in. Okay? All right. The worker nodes. This is the execution fleet. Let's shift from the brains to the brawn, the worker nodes. These are the Google Compute Engine VMs provisioned and managed by Kubernetes. They run your actual application containers inside units called pods. Each worker node comes preloaded with key components. The container runtime, usually containerd, responsible for pulling container images and launching them. Kubelet, the node agent. It talks to the control plane, registers the node, watches for assigned pods, and makes sure containers are healthy and running. Kubeproxy. This handles networking and traffic routing. It listens for service definitions and configures rules that allow pods to talk to each other and receive traffic from outside. Please note, Kubernetes worker nodes in GKE are Google managed VMs, and you can auto-scale them, resize them, or even mix machine types across node pools. So let's register the clusters to the fleet. And go to the networking. So resource management on nodes. It's important to remember not all the resources on a node are available for your workloads. Kubernetes reserves a portion of CPU, memory, and disk for system processes, such as kubelet, container runtime, and networking daemons. The rest is available to your containers through the scheduler. So if a node has 8 vCPUs and 32 gigabits of RAM, you might only see 7.5 vCPUs and 30 gigabytes as allocatable. That's why setting resource requests and limits is so important. Kubernetes uses those to schedule pods appropriately, avoid overcommitment, and maintain cluster health. So, summary for the exam and real use, let's go for this. The control plane. The purpose is to run the API server, scheduler, and controllers. The worker node runs user-defined workloads inside pods. The kubelet, it's a node agent that ensures containers are running. Kubeproxy maintains network rules for service routing. Container runtime pulls and runs containers. Reserved resources. This is the system overhead not available to workloads. So behind the scenes, what happens when you deploy? Let's say you type the following, and let me open up this. Authorize. Okay. Let's say you type kubectl apply f deployment dot YAML. Here's what happens when you do this. This request hits the API server. The control manager ensures the desired number of replicas. The scheduler finds the best fit worker nodes. The kubelet pulls the container image and starts the pod. The kube proxy updates routing rules so other services can reach it. All of this happens in seconds, automatically and reliably. So the pods. These are the automatic smallest unit in Kubernetes. Let me move this down a little bit. Okay. All right, set these. Enable private nodes. No, we're not going to do that. Okay, so we'll set this at 10.0.0.0. Oops. Okay, 10.0.0. Let's say 100. No, 0.100. All right. Only 4. Okay, that gave it. This is 192. 168. 0.0, right? 168.0.0.16. So 16. Okay. Auto provisioning networking tags. Just tools. Entertain. Okay. Next. All right. What is a pod? This is the most powerful building block in Kubernetes. A pod is the smallest deployable unit in Kubernetes. It represents a single instance of a running process in your cluster. But unlike virtual machines, pods are incredibly lightweight and transient by design. Each pod encapsulates one or more containers that are tightly coupled. These containers have several properties. They share the same network namespace, meaning they use the same IP address and port space. They share storage volumes, so files written by one container can be read by another, and they are always co-scheduled, so they run on the same worker node and are managed together as a single unit. This makes pods ideal for tightly connected helper processes. For example, you might have one container running your web server and a second sidecar container for logging and caching, both living inside the same pod. Let's get a good, let's see. No, that's internet gateway. All right, this should give you a good example of what this looks like. All right, so this makes the pod ideal for tightly controlled, connected helper processes. All right. So pods are ephemeral. Now, here's something critical for your understanding the exam and pods. Pods are ephemeral. They're not designed to be permanent. If a pod crashes or the node it runs on fails, Kubernetes doesn't attempt to repair it. Instead, it replaces it. The orchestrator ensures that the system returns to desired state, not by fixing what's broken, but by rescheduling a fresh pod elsewhere in the cluster. This is that's the magic. That's the magic. That's the magic of declarative infrastructure. You don't fix infrastructure manually, you let Kubernetes handle it. You don't manage pods directly. While pods are the execution unit, you almost never create or manage pods manually. Instead, you declare higher level resources like deployments to manage long running apps with rolling updates and version control, replica sets to ensure the correct number of pod replicas are always running, stateful sets for managing stateful pods with identity and storage consistency, jobs and cron jobs for one time or recurring batch workloads. These controllers generate and manage pods on your behalf. They abstract away the need for you to babysit ephemeral infrastructure. So what's the pod lifecycle? This is controlled by the controllers. Here's how the pod lifecycle works in practice. You submit a deployment YAML, and let me see if I can get that. Yeah, this would be a good example. A deployment YAML. Da, 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 da. There we go. No, wait. Let's say a deployment YAML. Okay. You submit a deployment YAML. Kubernetes creates a replica set. Okay. Let's see. Creates a replica set, which is responsible for maintaining a set number of pod replicas. Let's see if I can get this. Replica set versus a deployment YAML. You can see this. All right. The replica set ensures that if a pod dies or disappears, a new one is spun up in its place, often on a different node. During upgrades, rolling updates replace old pods with new ones gradually without downtime. So when we talk about scaling your application from 3 replicas to 10, we're really talking about instructing the replica set to maintain 10 live pods and letting Kubernetes do the rest. So if Kubernetes were an airport, the pod is like an airplane. Containers inside the pods are like the crew and passengers. The node is the runway. And the control plane is the air traffic controller, coordinating which airplane takes off, where it lands, and when it's replaced if it crashes. Pods get you from point A to B, but the orchestration ensures smooth takeoff, recovery, and rerouting if something goes wrong. So for the certification, here's what you should know. Identify that pods are ephemeral and stateless by default. Know that you don't manually manage pods. Deployment and stateful sets do that for you. Understand how pods share IP addresses and storage internally. Recognize that each pod gets its own IP address, even if it contains multiple containers. With this understanding, you now know what gets deployed when you run your application in GKE. You define a deployment, Kubernetes schedules pods, and each pod runs your containers with shared access and automatic orchestration. So, so how do you administer this cluster with node pools? In Kubernetes, scalability and flexibility aren't just features, they're foundations. So how do you manage those hundreds or even thousands of virtual machines that run your containers while still keeping costs in check and workloads predictable? Welcome to the concept of node pools. When you create a Kubernetes cluster in Google Kubernetes Engine, you're not just spinning up random instances. You're actually creating a node pool, a group of identical compute engine VMs that serve as worker nodes in your cluster. Each node in a pool shares the same configuration. The machine type, like E2 medium or N2 standard 4, or whatever. They can be larger or the smaller, right? This is where it depends on workload, right? The disk size and type, so you're talking about the SSD versus HDD, the taints and labels, right? These start to describe what it is and how to work it and identify it and regulate it. And then the image type. So this could be like a containerized, optimized operating system or Ubuntu. This uniformly simplifies scheduling, monitoring, and scaling and makes sure workloads are deployed predictably. So why use multiple node pools? Here's where node pools become a strategic advantage. You can create multiple node pools, each tuned to a different kind of workload. So let's break that down. A high memory pool might host analytics workloads that run big data jobs in Spark. A GPU-enabled pool might run machine learning models in TensorFlow. A preemptible pool might handle short-lived batch jobs for a fraction of the price. So you need fast storage, create a new node pool with SSD-backed disks. You need to isolate workloads by compliance boundaries, use taints and tolerations with separate pools. With node pools, you're not just scaling more, you're scaling smart. Rolling upgrades and targeted maintenance. Node pools also enable rolling upgrades and targeted maintenance. Why? Instead of updating the entire cluster and risking downtime, GKE to upgrade individual node pools one at a time. This means critical workloads may remain stable. You can validate new versions incrementally. You minimize risk to production environments. And yes, GKE supports auto upgrade, auto repair, and auto scaling at the node pool level. Just set it and forget it. So here's a tip for the exam. You want to remember that a node pool is a collection of nodes with the same configuration. You can have multiple node pools in a single GKE cluster. You can use different pools for different workloads. For example, a CPU bound versus a memory bound. Node pools can be scaled independently. Autoscaling kicks in based on CPU, memory, or custom metrics. And GKE upgrades the control plane separately from the node pools. So behind the scenes, how node pools help GKE's scheduling. When you submit a deep deployment to GKE, the Kubernetes schedule looks for nodes that satisfies the pod's resource requests: CPU, memory, disk, labels, taints, and affinity rules. Node pools give you that flexibility. You want to pin a pod to a specific pool, use node affinity rules. You want to keep some workloads from certain nodes, use taints and tolerations. Node pools become the architecture scaffolding of all your Kubernetes infrastructure. So in summary, node pools mean flexibility, control, and optimization. To recap, a node pool is your base unit of compute infrastructure in GKE. You can create as many node pools as needed. Each pool can be configured independently, and you can apply auto-scaling, upgrades, and affinity policies at the pool level. This is where Kubernetes shows its power, not just in orchestrating containers, but in giving you the knobs and dials to fine-tune your infrastructure based on real business needs. Stateless applications, lightweight and replaceable. In a perfect world, every application would be stateless. Spin it up, shut it down, scale it up, move it across zones, and never worry about data loss. But in reality, we live in a world where full of databases, log processors, message queues, and data pipelines. And those they need to remember. That's why the distinction between stateless and stateful applications become critical in Kubernetes. Stateless applications are the purest form of cloud native workloads. Think REST APIs, front end web servers, or microservices. They don't store session data. If the container crashes, Kubernetes just spins up a new one, no harm done. You can scale them horizontally, distribute them across the globe, and let Kubernetes manage the lifecycle without worrying about data loss. So stateless means resilient and fast. Stateful applications. Stateful applications, these are the kind that need to store data across sessions. Databases like PostgreSQL or MongoDB, log aggregators like Elasticsearch, or custom apps that store files, queues, or user sessions. These applications can't just disappear and come back like nothing happened. They require durable storage, accessible even after a pod is deleted or a node is restarted. And that's where Kubernetes gives us persistent volumes and persistent volume claims. Persistent volume claims and persistent volumes. Let's break this down. A persistent volume is a piece of storage in the cluster, like a Google Cloud persistent disk, provisioned by an admin or dynamically by Kubernetes. Persistent volume claim is a request for storage from a pod. It's like saying, hey, Kubernetes, I need 250 gigabytes of space. Please mount it into my pod. When you create a PVC, right, a persistent volume claim, Google works behind the scenes to automatically provision a persistent disk and bind it to the pod that needs it. And it's defined declaratively via YAML. Let's see if we can see this. Oh, all right, let me see. Get you an image for this. All right. So behind the scenes, to automatically provision a persistent disk, it's all declared via YAML. So let's create a persistent volume claim. So an example of this, let's see if we have this. Okay, this is a good example. All right. So the persistent volume and the persistent volume claim, right? In this, you'll create the YAML file tells Kubernetes create a volume that can be mounted by read write once, right? By one node. Let me see. And it should be 1 gigabyte in size. Okay, so you can apply it with the following command: oops, let's see, kubectl apply f pvc.yaml, right? And you'll have this apply this to Kubernetes cluster in the environment. And so Kubernetes will then provision the disk and make it available to your pods. Access modes, know them for the exam. There are three main access modes, and they do appear in the exam. There's read write once. This is mounted as read write by a single node. Read write many. This is ROX, ROX. This is mounted as read only by many nodes. There's read write many. This is mounted as a read write by many nodes. Note, this is not supported by standard GCP persistent disks. You'll need file store or third party storage. So knowing when and where to use each is a sign of strong architecture knowledge. So mounting a PVC to a deployment. Okay, so you've got the PVC. How do you attach it? You update your Kubernetes specs in two parts. Let's see if I can find this on here. Hmm, So volume mounts. Okay, so volume mounts. Let's see this. Okay. All right. So Let me see if this has the code for it. No, it doesn't, unfortunately. Kubernetes. Maybe I have to be more specific. This looks like it. Yep. Okay. So, all right. Let's see if this has some code. All right. This looks good. Volumes. Yeah. Volume mounts, Redis storage, data Redis. Okay. So in this, you add volume mounts in the block in the container selection, right? And declare the volume in the volume section, right? So this is the volume mounts, and this is where you declare the volume in the volume section, and you apply it with the following: vector edit deployment. Oops, deployment for my web app one. Say it's for your web app that's already going, and then Kubernetes will apply it to your web application. All right, and then you can verify that it's mounted correctly with the following code. All right, kubectl or kubectl exec it my web app to your pod ID, and then it would hit the bin bash, right, which shows it's executable. When it's inside the container, you'll type the following. Okay, dfh, and then if this, you'll be able to see the mount listed with the amount of space that's mounted, and just like that, your app has persistent storage. So here's a summary of when to go stateful. In the big picture, you use stateless containers for microservices, front ends, or APIs. You use stateful containers for databases or any app that must persist data. Use PVCs and PVs, those persistent volume claims and persistent volumes, to bridge the gap between ephemeral containers and durable storage. Know the access modes and how to define YAML and how to bind storage to pods. Okay. So far, we've built up a solid foundation of Kubernetes. You've launched your cluster, you've deployed your pods, attached persistent storage, and everything's humming. But now comes a vital question. How do clients actually reach your services both inside and outside the cluster? And that's the role of Kubernetes networking. And in Kubernetes engine, this is the part that is elegant, flexible, and production grade right out of the box. So let's break it down that in Kubernetes, pods are ephemeral, they come and go, which means you can't rely on pods IPs to connect them. So let's go back to this. All right. Okay. All right. You can't rely on the IP to connect them. Instead, Kubernetes introduces a higher level abstraction called a service. Right? A service gives you a stable IP address, a DNS name, and but depending on service type, it controls where and how traffic gets routed. So there's three Kubernetes service types, right? The three primary ways. Let's see. Hold on. Okay. The cluster IP internal only. This is the default service type. It exposes your application inside the cluster only. There's no external access. Think microservices and microservices communicating with each other. You'll often use cluster IP for internal APIs, shared caches, or interdependent backend components. An example would be a front-end service making a request to a backend database service via a cluster IP endpoint. Okay. All right, let's go from here. All right. NodePort. This is number two. Expose on every node. So NodePort takes it a step further. It opens a specific port on every node in your cluster. Traffic to a node's external IP on that port is forwarded to the appropriate pods. It's a simple way to test services during development or expose apps without provisioning a full load balancer. But keep in mind, port numbers must fall in a specific range, typically 30,000 to 32,767, and it's not ideal for production, especially in multi-zone clusters. Number three would be the load balancer. This is the GCP native internet ready. Now we're talking enterprise. With load balancer service type, GKE provisions a fully managed Google Cloud load balancer. It assigns a dedicated external IP and it automatically routes traffic to the backend pods. This is the go-to choice when your service needs to be reachable from the public internet and securely and at scale. So for this use case, you'd have a publicly facing API, web application, web applications, or any service that must serve clients around the world. So let's see the traffic flow in action. Let's walk through what happens when somebody hits that public IP in their browser. A client would send a request to your load balancer's external IP. GCP would route the request through its global network. The load balancer forwards the traffic to a cluster IP. The cluster IP maps to one or more nodes. Each node sends the request to the correct pod. So in this, the load balancer to the cluster IP to the node to the pod in action. And you don't have to configure any of this manually. GKE handles the orchestration under the hood. Here's a small bonus. Internal load balancer. If you need to keep your traffic inside your VPC only, you can annotate your load balancer service with something like this. cloud.google.com/load-balancer-type, internal, end quotes, right? This creates a private GCP load balancer that's only accessible from within your VPC. This is great for secure microservices that shouldn't be exposed to the world. So to recap, when and what to use. For the cluster IP, this is best for internal traffic only and exposes to inside the cluster. The NodePort is best for basic external access, and it's good for node external IPs. It exposes to node external IPs, excuse me. The service type for load balancer is best for production-ready internet access, and it exposes to global clients. And then there's a service type for internal load balancer via annotation, right? This is for private GCP traffic only. And this is exposes to VPC only access, all right? So after exposing your application, let's give it a quick try and show you. You can deploy your service with the following command. kubectl get svc service, right? With this, you'll see cluster IP external, if any exists. I don't think I have a Kubernetes cluster loaded. If I do, then I'll be paying. I'm paying for it. All right. You'll see the cluster IP, external IP, if any, and port mappings. You want to visit your app. If it's a load balancer, let's see. I think nothing is loaded. Okay. Okay, you could use. I don't think it's going for anything, but that's okay. That's good. That's good. I'll come back to that, right? Okay. You could also use the following. Okay, so there's none. Okay. Perl, HTTP. You can use this, and Kubernetes will do this, right, for the external load balancer. So in summary, Kubernetes gives you stable endpoints for dynamic workloads. All right, and you can choose the right service type, the internal cluster IP, the node level node port, or full external load balancer. The GKE will integrate natively with Google Cloud Load Balancing to provide secure global scale routing. And all of this is declarative, repeatable, and can be defined as a YAML. All right. Let's go. Okay, high availability starts with cluster design. As your application grows, all right, as your application grows, as your application grows and serve users across continents, reliability isn't a bonus, it's a baseline. That's where Kubernetes cluster topology becomes a strategic decision. So let's expose and explore how multi-zone and regional clusters in Google Kubernetes Engine helps you build highly available production-grade environments. By default, when you create a Kubernetes cluster in GKE, you must choose between two deployment models, zonal or regional. These are different cluster types, okay? Not on this. Let's see. Okay. I see zonal here. If you see zonal, let me know. Zone, reach, access IP from any ranger. No, regular. No, it's not here. Okay, that's okay. It's not up here. Okay, zonal and regional. While both provide redundancy, they differ significantly how the control plane, the brain of Kubernetes, is deployed and managed. So let's walk through each. Zonal clusters. In a zonal cluster, the setup looks like this. The control plane is deployed in a single zone. The worker nodes can either be in the same zone, single zone, or span multiple zones within the same region. So this will be multi-zonal. This gives you basic zonal fault tolerance for worker nodes in a multi-zonal setup. If a zone hosting your worker nodes becomes unavailable, workloads can be rescheduled to other zones as long as your control panel is still online. But there's a catch. If that single zone control panel fails, or control plane fails, or the zone goes down, you lose cluster level management access. Your workloads might still run, but you can't update, scale, or deploy anything until control is restored. So zonal clusters are simpler, cheaper to run, ideal for development or less critical services. But for mission critical applications, we need something bigger and stronger. That would be regional clusters. The regional cluster, this is GKE's fully managed high availability solution. When you choose a regional cluster, Google automatically deploys the control plane 3 times, once in each of the 3 separate zones within a region. Your worker nodes are also distributed across 3 zones by default, meaning your cluster remains fully operation even if a zone or even 2 go offline. Your control plane is highly available. Your workloads benefit from automatic balancing across zones. And better yet, upgrades and maintenance are seamless. GKE handles them sequentially across zones, minimizing downtime and risk. So how do you choose between them? Here's the critical detail. You cannot switch a cluster from zonal to regional or vice versa once it's created. This is a foundational decision. Make it carefully. If your use case involves global users, compliance or SLAs, business critical APIs, then regional is worth the investment. If you're experimenting, running dev environments, managing isolated batch workloads, then a zonal cluster is simpler and more cost effective. So here's a real world example. Let's say you're running a retail analytics platform for stores across North America. You deploy a regional cluster in US Central 1 spanning zones A, B, and C. One day, US Central B experiences a disruption. No problem. Your control panel maintains activity in A and C. Your workloads automatically reschedule using node pools in the healthy zones. End users never experience a blip. That's the power of regional clusters. So here's a quick quiz. Which cluster type deploys multiple control planes across zones? Regional. I hope you got that. So in summary, you have 4 different features. The control plane, which is a zonal cluster in one single zone, and a regional cluster for 3 distributed across, so it distributes across 3 zones. You have fault tolerance. This is for worker nodes only in multi-zones. The control plane and the worker node. You have costs. Why? This is lower. In a regional cluster, this will be higher with more infrastructure. The use case for zonal cluster would be dev or test. For a regional cluster, it would be production or high availability. The flexibility for a zonal cluster would be that you cannot convert post-creation. And the flexibility for a regional cluster is that you must choose this upfront. They're pretty much the standard on that one. So that wraps up your introduction to Kubernetes cluster availability on GKE. In cloud computing, efficiency isn't just about performance, it's about price performance. This is where preemptible instances, which are cost-effective batch processing, comes into play. When you want to stretch every dollar while scaling compute-heavy workloads, there's a powerful yet temporary ally in your toolkit, preemptible virtual machines. So what are these? These are short-lived virtual machines offered by Google Cloud at a fraction of the cost of standard instances. But there's a catch. Preemptible VMs only live for up to 24 hours, and they can be terminated at any time. If Google needs the underlying hardware for other customers, there you go. So these are ideal for workloads that are stateless, meaning they don't need to remember previous action, interruptible, they can start or restart or resume from a checkpoint, or batch oriented. Think data processing, simulations, log crunching, and rendering jobs. And when you combine them with the scheduling intelligence Kubernetes, you get cost-effective, fault-tolerant scalability. Why use preemptibles in Kubernetes? Well, because they can be deployed throughout the dedicated node pool. So here's how it works. You define a node pool with the preemptible flag enabled. Kubernetes schedules pods, your containers on these nodes, and ideally pods that are stateless, retriable, or ephemeral. When Google Cloud reclaims the VM, Kubernetes detects the preemption and simply reschedules your pod on another available node. There's no manual intervention, no babysitting jobs, and no high costs, just savings and smart orchestration. The real cost benefit is that preemptible VMs cost up to 80% less than standard VMs of the same configuration. So imagine scaling a machine learning model across 100 preemptible nodes during a training cycle, then tearing them down automatically once the job is done. That's enterprise-grade processing power on a startup-friendly budget. So how do you use this? Let's say you want to create a node pool with a preemptible instance in your GKE cluster. You could run the following. I'm just going to copy and paste this from my little sheet and show you. Okay. Okay. So you see this G Cloud container, node pools, create a batch pool. The cluster would be for the GKE cluster. The machine type would be E2 standard 4. The number of nodes, 4. They're preemptible, and they're US Central 1B. Okay? This creates a four-node pool named batch pool using preemptible E2 forward standard 4 VMs, E2 standard 4 VMs, and you can then label or taint the node pool to ensure that only specific pods are scheduled there. The nightly log processors are one-time ETL jobs. So best practice would be this: to make most of your preemptible VMs. Use taints and tolerations to avoid accidentally scheduling critical apps. Pair them with horizontal pod autoscalers to respond to spikes in demand. Combine them with persistent storage if jobs need to resume from a saved state. Run CI/CD pipelines, rendering workloads, or batch video encoding where interruptions are okay. So things to watch out for. Preemption isn't predictable. Your VM might live for 20 minutes or nearly the full 24 hours. Stateful apps won't survive. So use standard nodes for databases or caches. Spot capacity is not guaranteed. During demand spikes, GCP may not offer any preemptibles. So here's a couple of features to remember. The max lifetime is 24 hours. The cost up to 80% cheaper than standard VMs. It's best for batch, machine learning, training, stateless applications, scheduling. This is via preemptible node pools, and the preemption behavior, they can be shut down at any time. So GKE Autopilot, the fully managed Kubernetes experience. Let's see. Let's go back to this since I didn't do this. Let's see if I can find this. Autopilot, there we go. So you have Autopilot. All right, let's see this. So while standard GKE gives you tremendous flexibility and control of your Kubernetes clusters, what if you're in the mood for an even more hands-off experience? One where you focus on exclusively your workloads without worrying about node management at all. That's where GKE Autopilot comes in. What is Autopilot? It's a fully managed Kubernetes service that abstracts away the underlying infrastructure completely. You simply create an Autopilot cluster, deploy your workloads, let Google handle the rest. Autopilot automatically provisions and manages nodes based on your workload requirements, configures nodes with optimal settings, handles node health and scaling, automatically applies security best practices, and maintains node versions and upgrades. You pay only for the resources your pod actually use rather than for the entire VMs. All right, so let's see. Go back here. Oh, so this is what I have for here. Autopilot. That's what I had set up for that. So it's automated. Okay. So you use Autopilot when you want to want maximum operational simplicity. Your workloads are standard and don't need special node configurations. You want to focus exclusively on application development, and your cost optimization without node management is important. You choose standard GKE when you need specialized node configuration for GPU or custom machine types. You want fine-grained control over node pools and settings. You want workloads your workloads have specific infrastructure requirements, or you want to run specific node level daemon sets. Okay, so Autopilot optimization. So Autopilot clusters automatically optimize resources to fit your workloads perfectly. Pod sizing. Your resources requests determine how Autopilot provisions nodes. Automatic scaling. Nodes are created and deleted automatically as demand fluctuates. Cost efficiency. You pay only for vCPU, memory, and storage your pod requests, not for entire VMs. This means you get better resource utilization without manual tuning. So looking ahead, Kubernetes best practices. So when you build applications on GKE, consider these architectural best practices. Design for failure. Assume pods can and will be terminated. Use deployments, stateful sets, and storage properly. Resource management. Set the appropriate CPU and memory requests and limits for all containers. Liveness and readiness probes. Implement proper health checks to enable Kubernetes to Effectively manage your application lifecycle. Service networking. Use the right service type for your needs and leverage GCP's load balancing capabilities. Security posture. Follow the principle of least privilege with RBAC, that's role-based access, control, network policies, and secrets management. Stateless when possible. Design applications to be stateless where possible and use appropriate storage abstractions when state is needed. Observability. Implement proper logging, monitoring, and tracing to understand your application behavior. These principles will guide you towards building resilient, scalable, and efficient applications on the Google Kubernetes Engine platform. GKE Enterprise, advanced features for complex organizations. For large enterprises, this is what would be selected, right? With GKE Enterprise, formerly Anthos, provides additional capabilities that extend beyond GKE. This is multi-cluster management. This administers multiple Kubernetes clusters from a single control panel. Multi-cloud and hybrid deployments that run consistent Kubernetes environments across GCP, other clouds, and on-premises. Config management, which implements GitOps workflows for consistent cluster configuration. Service mesh, which is advanced traffic management, security, and observability with Istio. Policy controller. This enforces organizational policies across all your clusters. These capabilities help enterprises standardize their container approaches across diverse environments while maintaining governance and control. Okay. CI/CD integration with Cloud Build and GKE. Building a containerized application is only half the story. You also need a robust workflow to build your container. Ah, you need a robust workflow to build your container images, test your applications, deploy reliability on your GKE clusters. How do you do that? All right, let's go over here. Cloud Build. All right. What is Cloud Build? Google Cloud provides integrated tooling for continuous integration and delivery with Google Cloud Build. This is a fully managed CI/CD platform that executes your builds as a series of container steps. All right. There's cloud source repos with fully managed private Git repositories. There's artifact registry where you can store, manage, and secure container images. And a basic CI/CD pipeline for GKE might look like this. 1, developers push code to a cloud source repository like GitHub or GitLab. 2, Cloud Build automatically builds a container image, runs tests, pushes to artifact registry, updates Kubernetes manifests, applies changes to GKE clusters, and then 3, GKE handles the rolling update of workloads with zero downtime. This automation ensures consistent, reliable deployments with full auditability. Okay. Container security in GKE. All right. Security is a critical aspect of containerized application. All right. GKE provides several built-in security features. Okay. Image security. This is a binary authorization. This ensures only trusted container images are deployed. Vulnerability scanning. This automatically scans container images for security issues. Container optimized OS. This is a hardened OS designed specifically for containers. Then you have network security. Network security includes network policies, so Kubernetes native firewall rules for pod-to-pod communication, private clusters, which run GKE with internal IP addresses only, and then VPC native clusters, which are better integration for GCP networking features. Next, you have workload identity. Workload identity means that this allows pods to authenticate as service accounts to access Google Cloud services. This includes secret management, which securely stores and accesses sensitive information. Next, you have cluster security. This includes shielded nodes that verify node integrity, control plane security, which is fully managed and secured by Google, and then auto upgrade, which keeps clusters running secure, up-to-date Kubernetes versions. These security features help ensure your containerized applications remain secure throughout their lifecycle. So, in conclusion, we've gone through the Kubernetes journey. We've covered the foundations of deploying containers on Google Kubernetes engine, managing cluster architecture, attaching persistent volumes, exposing applications through load balancers, and optimizing with node pools and preemptible instances. Kubernetes on Google Cloud gives you a powerful, flexible platform for running containerized workloads at any scale. With GKE, you get the benefit of Google's years of experience running containers in production with managed services that significantly reduce operational overhead. Whether you're deploying a simple web application or building complex microservices architecture, GKE provides the tools, patterns, and capabilities to run your containers effectively, securely, and reliably. As you continue your cloud journey, remember that containers in Kubernetes represent not just a technological shift, but an operational one as well. So embracing the principles of cloud native development and allowing your organization to move faster, scale more effectively, and build more resilient applications is critical. Here's a couple of exam practice questions. I'm going to give you the answers like I've been doing. Okay, what's the smallest deployable unit in Kubernetes? That's the pod. Okay, which type of Kubernetes service would you use to expose an application to the internet with a static IP address? That's a load balancer. What resource would you use to ensure a pod can access persistent storage even if it's rescheduled to another node? A persistent volume claim. Which type of GKE cluster provides the highest availability by replicating the control plane across multiple zones? A regional cluster. What type of VM can save up to 80% on cost but might be preempted at any time? A preemptible VM. So that concludes chapter 5. Next up will be operations in Google Cloud. This is observability with Stackdriver.